of Mathematics at the Courant Institute, New York University. He received her PhD from Université Paris-Sud. Her previous position included appointments at the Université Pierre-Emmanuel Jabin and École Normale Supérieure de Cachan. A large part of her work has focused on Ginzburg-Landau model of superconductivity and on understanding why and when vortices form triangular lattices. He has more recently turned her attention to questions of statistical mechanics of system with Colombo type repulsion also arising in approximation theory and a random matrix, and which turned out to be generalization of the questions addressed for the behavior of vortices in superconductivities. He was a plenary speaker at ICM in 2018 and is a recipient of EMS and Henry Bangalore Prize and of this major Bordeaux Prize of the French Academy of Science. Now let's welcome Professor Serfaty to give the talk. Sylvia, you can start.
And for this opportunity to present this topic. Please feel free to interrupt with questions, as I don't hear you all anyway. I don't see you all on the screen. And yeah, thanks very much to Hung for organizing this. And so I'm going to talk about mean field limits for systems with singular interactions. So I hope you can see my screen well. So the kind of question that I'm talking about here is I want to study systems of ODEs of, for instance, this form. So you have endpoints representing particles or positions in space, in some space, many other possible things. And their evolution is given by something like this form. 1 over n, sum of k, xi minus xj. So this is like if it's an ODE, but maybe I'm gonna make it possibly into a stochastic differential equation, an SDE, by writing it like this and adding some noise. Can you hear me? Is it okay?
Yeah, it's okay. Yeah.
Okay. All right, so here, you see, yeah, K is an interaction kernel. And you see that each particle is feeling a sort of average force. So here is the average, 1 over n times the sum. An average force generated by all the other particles, depending on, typically on their distances to the other particles. If you want, you can make this, you could have more general things, like things that don't necessarily on the red positions, but I'm going to be talking mostly about this setup. And so here, I'm adding a possible noise in the form of here, and ID Brownian motions. So each particle undergoes an added diffusion, but independently from the other ones. And then this beta here is an inverse temperature. So maybe you don't want to have temperature at all, then you take beta equals infinity. There is no temperature, there is no diffusion. And of course, we can consider this with an initial data. you know, at position x at 0 at initial time. And the kinds of case that I will be interested in particularly is when k derives from a potential. So what I mean by that is k is, for example, a minus gradient of some potential g. That corresponds then to a gradient flow. Or k maybe is some antisymmetric operator times gradient g. Or maybe some combination of the two. You could do some mixed flows. So some general operator, linear operator M, but then what you need is that mg grad g, what you need is that mxc dotted with xc has to be negative. So there is a lot of literature on the case where k is regular. You know, Lipschitz, to be particularly interested in the case where g is singular. And a particular case of the singular case is the Coulomb case. So the Coulomb case is going to be minus log of the distance dimension 2 and 1 over x d minus 2 if dimension is bigger than 3. There's also a 1D Coulomb case, but let's think of those. So you know the Coulomb interaction, which is fundamental interaction in nature. So it's of this form, and you see it's always singular. So when two particles are very close to each other, the force is singular, and it will materialize here into a very strong repulsion if you're looking at the gradient flow case, and here you will have conservation of energy. But okay, but also more generally, you might want to consider general inverse powers. So that's called the Rees case. So I will refer to this power S a lot of the times in the talk. So note that S equals D minus 2 in the Coulomb case. And we will take this convention that S is 0 corresponds to the logarithmic case. So logarithm is formally a sort of zeros power. And of course, you might be interested in other singular interactions. I will tell you a bit what we can say. Of course, what we want to understand is the behavior when n goes to infinity. So when the number of points or particles becomes very large. And the motivations are many. Yes. Pig mentioned that I was interested in vortices in superconductors. That is true, and this is actually how I became to be interested in these types of problems. So in physics, you encounter a lot of these systems of points with interaction, in particular equations of vortices. So vortices in fluids and in superfluids. And in that case, what you're really interested in this is this logarithmic two-dimensional case. So a particular case of Coulomb interaction. So this is D equals 2 minus log. For instance, the case where you look at K equals minus grad perp of log x. So you see what I mean by grad perp? I take the gradient and I rotate it by pi over 2 in the plane. So that's the Biot-Savart kernel, by the way. Then the system is called the point vortex system. And it's known, it's been very much studied in fluid mechanics, and it's known to converge as n goes to infinity to the incompressible Euler equation in the case without noise, without diffusion, in vorticity form. Or incompressible Navier-Stokes if you have the noise. Okay, so this is for physics, but there is also other things like computing, approximating minimizers of interaction energies. Right, so let's say you want to understand these types of interaction energies here, sum over all pairs of particles of G of xi minus xj. You see here, I have to remove, to take this from there, because otherwise here I would have 0. And G is infinite at the origin in my singular cases. So we always remove the self interaction. So this is an energy, right? We could call it Hn of Xn. And what I will call Xn here, that's a shortcut for the n tuple X1, Xn. Okay, so an interaction energy of this form, maybe with some potential, I don't know. You can add some sort of external potential, or confinement potential, it's called. Right, so if you have an energy like this and you want to understand minimizers, you might want to try taking the gradient flow of Hn, and then you find exactly the form of system I was talking about here. So people use this in particular in computation. So, for example, computations for optimal parameters of neural nets. So if you've heard about neural nets in machine learning, they correspond to actually doing some sort of steepest descent in a very, very large parameter space, the space of parameters of your neural nets. And when you do this steepest descent, it actually looks exactly like a system like this, but maybe not in the form xi minus xj, but in a general form k of xi xj with a comma. But in any case, people use this to try to compute. So I'm quoting, there's work by Bach and Shiza and Rostkopf and Van den Eyden that were the first to introduce this point of view of optimization of neural nets as a system of particles, of interacting particles, but also for potential theory. So it turns out that the continuum limit of Hn is something that's of this form, I'll call E of mu. It's a functional on probability measures, probability densities. And if I have a external potential, I add here V. And the minimizer is called the equilibrium measure. So it's an important object in potential theory, and people want to compute it. And so a way to compute it is to take these gradient flows of the discrete interaction energy and let it evolve for a long time and hope that it converges in large time to the minimizer of this. And then you have the version with noise. So instead of wanting to understand minimizers of this, you want to consider Gibbs states. So you want to consider this sort of probability laws of the form exponential minus beta hn. So hn is still in the same form here. And now you put it in the exponential with the temperature, inverse temperature beta. And Zn, as you may know, this is called the partition function. Partition. And it's just a normalization that makes this Pn a probability. Because you need to normalize. So then basically this law Pn corresponds to the invariant measure for these types of statistics, for these types of evolutions. Okay, so when you start from the distribution Pn and you run these dynamics, it's unchanged in time. So it just continues mixing the particles in the same way. So this is where you can connect with statistical mechanics. And there is a continuum version of this, by the way. Just like with the equilibrium measure, the continuum version is to minimize E beta. So you put the same things, but you add an entropy term here. So this is a sort of minimizer of this is called, actually, there is not a standard terminology, but I like to call it the thermal equilibrium measure. So it's a little bit different from the standard equilibrium measure because it has tails. So the standard equilibrium measure typically is compactly supported, and the thermal equilibrium measure is more regular, more smooth, and decays at infinity, typically like an exponential of something. Okay, so I should continue with motivations. I said approximating minimizers, and I should also say all sorts of modeling of collective behavior, which you encounter in economics, you know, where you have like agents and they interact. There's even these things called MeanField games now. Also biology, social sciences. You know, people want to understand aggregation, how species want to be close together or not, or flocking. But of course, all these things correspond to more general systems where the interaction is not necessarily singular, not Coulomb certainly, Coulomb is more of the physics type, and more general like K of xi, xj, and they want to consider things that are more typically attractive or attractive and repulsive. So for instance, like, you know, people like to congregate and be close to each other, but not too much. And so at certain distances, they prefer to be far. So there's all sorts of things happening in these forms, but there's a very large literature. And I can refer you to some review papers if you want. But just to say, there's a lot of motivation in these things. And I should have said in the physics part, so when you consider the statistical mechanics models, these are very important in physics. You encounter them, as I said, in statistical mechanics of Coulomb gases. So I should say, yeah, I should put Coulomb gases, which is one of my topic of research, random matrix theory, because you have certain forms of Coulomb gases that arise as random matrix model, etc. Okay, and then I want to mention also another type of questions of this form that you can ask, which is the second order models. So this time the evolution is going to be second order. So you said that the velocity dxi dt is equal to vi, and it's the derivative of vi, which is of the form that we said before. So it's the acceleration, if you want. Sum over I different from j, or I should say j different from I, of k xi minus xj dt. And if you want, you can add this noise dwi. So you see, now it's the acceleration that's equal to the average force. So again, mean field because average. And that is much more naturally a physics problem, right? Because you recognize Newton's law. So this is Newton's law of n interacting particles. So if you consider the case where k equals grad g and g is Coulomb, this is exactly the model for plasma physics, for plasmas. So it's a very important model in plasma physics. So this plasma physics is what you use, you know, the model for plasma is what's used to model stars. So in astrophysics, ionized matter, in which you consider that your electrons are free basically in your gas to move. So this is a very important problem. So as I said, what the problem that we're interested in is naturally to understand the large N behavior of these interactions. So do you have any questions at this point before I sort of finish with the motivations? But, no? And so we want to understand this large N limit, and how we're going to describe it. Well, there is two ways. And they are very related. One is to describe the empirical measures. So you form the empirical measure mu n at time t, right? It's going to be 1 over n, sum from 1 to n of the Dirac mass at xit. So this is the evolving particles. And you want to understand then the limit as n goes to infinity of mu and t. So you can call it mu t. So sometimes I will alternate. I'm sorry about my inconsistencies, but I tend to alternate between mu and rho. So sometimes it will be called mu, or sometimes it will be called rho t, or just always the density of particles. Right, and then there is another way of looking at it, which is to consider the law of the particles distribution. So this one I tend to call Fn of x1 xn, or Fn of xn. As you remember, big Xn is a shortcut for the n-tuple. And sometimes you could call it also PNT in analogy with this Gibbs measure statistics, right? So it's a law on the particle configurations, it's a probability law. And you say that you're given a certain law at initial time and you want to understand how it evolves in time. So for instance, you can say Fn0 is IID. So that's an example. It will be IID if you assume that it's of the form rho 0 x1 2 0 xn. So this is now IID with law rho. So all your particles at initial time are drawn independently with this law rho. But that's one possibility. You could put as an initial data the Gibbs measure that I put here, and then see how that evolves in time. Right? There's many possibilities. And so then you try to understand FNT. And how do you describe FNT? Well, it's not going to have a limit, right? Because it's a function on a space that's becoming larger and larger. Instead, you can understand its k-point marginals. So f and k. What is f and k? It's a function of only k points, where you have integrated out all the particles except the first k ones. So it's integral of fn, x1, xk, yk plus 1, etc. dyk plus 1, dyn. And I should have said at the very beginning that I want to assume that these laws Fn are symmetric. So it's symmetric, which means that if I interchain particles, it doesn't change, which means that, you know, I've labeled the particles, but it's not important. The law is just depending on the locations of the particles, right? Okay, so these are the k-point marginals, and then you can try to understand the limit of these k-point marginals as n goes to infinity for fixed k. So you freeze k and you let n go to infinity. Okay. So now what is the connection between the two? Well, you can actually sort of recover the k-point marginal laws from the empirical measures. So I think that the empirical measure point of view is sometimes called the Dobrushin point of view. And the law of particles, I don't know. But in any case, they are directly related, and this is well known. This is standard. And there is this important notion, which is called propagation of chaos. Yes. You know, Katz, I think, popularized it, but it goes back to Boltzmann also. And what is propagation of chaos? You say that there is propagation of chaos or of molecular chaos if whenever the initial law is tensorized, so tensorized means this IID distribution, rho 0 x1, rho 0 xn, which is the same as, I will call it rho 0 tensorized n times of xn. Then, so that's the initial data. If it's tensorized like this or factorized, then it remains the same at later times. Then the same happens at later times. That is that you're able to say that FNT x1 xn is now it's approximately equal. And here you can also ask approximately equal. If it's approximately that, then it's approximately of a form like that for a certain rho t that you have to determine. And of course, you cannot, well, it's not clear how to justify this, what this thing means. You should understand it in the sense of K-point marginals convergence. So more precisely, F and K, the K-point marginal. Now that you can say rigorously converges to something of this form. Okay, so if this holds, then you say you have propagation of chaos. That means if the particles are independent initially, they remain almost independent at later times. Of course, they cannot be exactly independent because we have to remember that the particles interact. So it's just because on average, they still remain approximately independent. It's because of the MeanField collective behavior. Okay, so now what I claim, and it's again a standard fact, is that if we show that there is a limit for the empirical measures, then we obtain propagation of chaos. So that showing that the empirical measures converge. That is 1 over n sum of delta xit has a limit in the sense of measures, and we also call it rho t from ut. Then so it's essentially equivalent to showing propagation of chaos in the above sense. Okay, so in fact, that means that, well, it's enough to worry about proving convergence of the empirical measures. So I will show it to you for one case. Okay, so for instance, show that so mu and t, which is the empirical measure, converge to rho t. Implies Fn1 converges to F, so actually to rho t. Okay, so that's the first marginal. So how do you show that measures converge in the weak sense of measures? Well, you take some smooth test function. So take phi, smooth enough, actually continuous would suffice. It's not really important. With compact support. And test Fn1 minus rho t against phi. Right, so you want to show that this goes to 0 if you know convergence of the empirical measures. So I can rewrite this. I can use the symmetry of Fn to say that this is the same as doing this. I'm going to go on the next one. Yes. Okay, now let's do the average of sum of phi of xi. Okay, so if you want, you can unpack this, right? So unpack this thing, you find sum phi of xi, fn, x1, xn. You can integrate out all the variables except the first one, and you find exactly this against this. Since you divide by n, it's the same. And now you can subtract integral of rho t phi. That subtracts exactly this thing off. It's independent of the points anyway. And now you can integrate that. You should integrate that with respect to x1, xn. Okay, so you check that if you do this integral, this integral actually collapses onto this by symmetry and definition of the marginals. And so now this term, you recognize this is the integral of phi tested against the empirical measure minus rho t. And so if I assume that the empirical measure converges, then I know that this goes to 0. And then I'm just averaging with respect to Fn, something that goes to 0. So it goes to 0. Okay. So it's proving that the first marginal converge. So then you can try to do this for higher order. So for k-point marginals, and I will show you a sketch of it because why not? So now you want to understand f and k minus rho t tensor k times against a function phi, the test function, which now has to depend on k variables. And you rewrite this again as some integral against Fn. Now, depending on all variables. And what do I put here? Well, you have a little bit of combinatorics to look at, a little bit more combinatorics. So you have to look at all the ways of extracting k particles. I should write this something like this, minus rho cancelled k times phi. Okay, so it's the same type of thing, if you unpack this, you're gonna find the rho t phi, and here you're gonna find all the possible ways of finding k particles, phi times fn, and again by the symmetry and the definition of marginals, the same as this. Okay, and so then we rewrite this as integral of fn. We're averaging with respect to the probability fn of this. And now we can write this sum as basically an expansion of a sum to the power k. So it's this against phi. You see, because when you expand this tensor, you find exactly these types of k terms. Okay, so now all that remains to show is that these guys, these things go to 0. And you remember, you know that the empirical measures converge to OK, so then you're really right. It's actually not a sketch, it's really the proof. So this you rewrite, and just like your laws, basically. So you can factor this, and then you can get things like this in factor. Okay, so every time you can refactor inside these differences, AK minus BK, you can factor A minus B, right? Just like in standard calculus. And so because you factor out this thing, this one goes to 0, and this one you have bounds. And so you're good. Okay, so this is this is showing this sort of equivalence between these 2 points of view, or at least I showed you one direction, proving convergence of the empirical measures and proving propagation of chaos in the sense of convergence of the k-point marginals to factorized states. Okay, so now I will finish for this first lecture by discussing the formal limit. Okay, so what is the formal limit, which means what is the rho t we should expect? Yes. The correct rho t. Once we've guessed the correct rho t, we can hope to prove convergence to it. Okay, so for there is a general fact that I remind you, which is that you have this relation. If you have a point that moves x of t, position x of t that's moving, you have a Dirac mass at this point, then the time derivative of the Dirac mass is minus the divergence of the velocity of the point times the Dirac mass. So this is basically in the sense of distributions, right? So it's just an application of definition of distributions. If you're in doubt, try it against the test function, differentiate phi of x of t, and you'll find this. Okay, so that's if you want a continuity equation. It's another way of calling it. So if we have convergence of the empirical measures, which is the convergence of Dirac masses, what we expect is that it's going to solve something like this, dt rho. So I take all these relations, I add them, and I divide by n. So dt rho should be solving plus divergence of rho, right? So this is going to be from the Diracs. And then here there should be the, I should put the velocity somehow. So here I need to put velocity, the average velocity. And now I look at what my law for the velocity is. So I'm talking here only first order. So first order, you see that the velocity, you can express it with the empirical measure, more or less. It's k convolved with the empirical measure, because you're summing over all the other particles. So if you take the limit formally, you can expect that this is going to be k convolved with the limit. The velocity, this should be dt rho plus divergence of k convolved with rho times rho equals 0. But that's in the case without noise. Huh? That's for beta equals infinity. So here I'm being a little bit hand waving because I've taken, this is sort of taken the limit of 1 over n sum of k x I minus xj to k convolved with rho. And that is certainly a little bit exaggerated because we have nonlinear terms, in fact, and we have the possible singularities of k. So you see that, so this is not legitimate or not rigorous because of the nonlinearity. The nonlinearity is that you have this product, right? You're taking, you're saying you have this thing converges and this thing converges and then the product converges because of product. So there's nonlinearity and because of the possible, I mean, you see right away that as soon as k is not smooth, it's going to be more difficult. However, it is the right equation, and this is what we're going to have to show, that we have convergence to this. Of course, if it's with noise, with diffusion, where you add a corresponding term. So this is the MeanField equation. People who do quantum mechanics, they would call it the Hartree equation. But with noise, you will have the same, except you pick up a Laplacian corresponding to the diffusion, which of course is the thing you would expect if you know a bit of stochastic calculus, right? Or Ito's formula. You know, the Brownian motion is going to give you a Laplacian in the equation, just like the heat equation is the equation associated to Brownian motion. So you get an extra 1 over beta Laplacian rho, which is not bad actually, because we like to have Laplacian in our equations because it smoothes the solutions, right? It regularizes the solutions, whereas here it's less clear. So this is from the point of view of the empirical measure convergence. Okay, so now what about the k-point marginals point of view? Well, in that case, you note that Fn solves something that's called the Liouville equation sometimes. I think it has other names, but which is dt of fn plus sum from 1 to n of gradient with respect to the variable xi. And here you have the full thing, sum of k, xi minus xj, j different from I, and you put fn again. So it's of the same form. Huh? And if you have noise, you have a right-hand side. To this. You have a sum of Laplacians. Again, with respect to variable xi. Okay. So you need a little bit of Ito calculus to show this, but if you are familiar with it, it's not too hard. And then again, now you can start to try to take limits of f and k in this relation. So the problem that you encounter is that when looking at the time derivative of the k-point marginal fn, you see right away from this equation that it's going to involve actually the k plus 1 point marginal. So if you want to understand what happens to 1 point, you have to understand what happens with 2 points, because this 1 point is going to interact with another point every time, one by one. So when looking at dt f and k, we find expressions that involve f and k plus 1. And so then if you want to understand f and k plus 1, you have to understand f and k plus 2, etc. So it's a sort of recursion. And this is called the BBGKY hierarchy. It's a case of that. And usually such things are difficult because, well, it's hard to close all the way to the end of the hierarchy. So not obvious, but still formally, you expect that these f and k, if you plug in formally in these equations, you expect f and k converges to rho t times k times for the same rho t's as I boxed above, for the same rho t in the boxed equations. And of course, this is normal because we've already seen before that the 2 points of view should be equivalent, so they have to give the same limit. Okay. And then I want to mention the second order case. Remember where you consider velocities, derivative of the positions of the velocities, derivatives of the velocities are given in a MeanField form. Well, to describe the second order case, we have to go to kinetic formulation. So in kinetic formulation, we're going to study again densities of particles, but also densities of particles and velocities. So it's going to be x1, xn if you want, and velocity is v1, vn. So densities so it's in position velocity variables if you want. Okay, so you imagine you're given an initial distribution of positions and velocities, and you want to understand how that evolves in time. Well, you expect that there is convergence again of the marginals to some f and k converge to f. So k times where ft solves this one, df dt was v dot grad x f plus k convolved with rho grad vf equals 1 over beta Laplacian vf. So that's if you have the diffusion. Of course, you can always take beta equals infinity. And this is a kinetic equation. This is a Vlasov equation, and it has the diffusion part, the Laplacian. Usually you call it also Makin-Vlasov. If K derives from the Coulomb potential, then it's called Vlasov-Poisson or Makin-Vlasov-Poisson. And as I said, deriving, well, I didn't say it completely, but deriving this equation from the n-body dynamics is considered one of the big open questions. All right, so you want to derive effective from the n-body dynamics. So there's been also certain literature, certain progress at deriving these equations. So maybe I will keep that for next time, because I see that we're getting a little close to the end. But okay, so next talk, which is tonight for those of you who are in Asia. Yeah. This afternoon for people in Europe. And this morning for people in America. Yeah. Exactly. So for this night session, I will describe different strategies for proving the convergences to these equations, and what results have been already achieved. And then probably tomorrow I will start describing new strategies, etc. So if you have any questions at this point, it's a good time. Yeah. So any question or comment for speaker? Yeah, can you see the chat? There's some question from Bin Wang. In the chat, I see. Yeah. Yes, maybe I messed up my coefficient. Very good point. Yeah. Yes. The coefficient. There should be a 1/2 first of all. Let me check. I never pay attention to this. If I put the beta. I have it written properly somewhere. Yes. done is I should have put the square root. That's why I should have put a 1 over square root in the first thing. It would have been more correct. So here I should have put a square root. Okay. And then I should have put other things I should have done. I should have put a 1/2 here. 1/2 here. 1/2 here. And then I should have put 1 over 2 beta. Where's my one? Here also the square root. And then I think there's a 1/2. Yeah, are you now in agreement? And here also 1/2. Everybody okay now?
Yeah, I think okay. Any more question for speaker?